Okay, this is the second part of Chapter 7, and today we're going to be talking about ionization energy and what's called electron affinity. This is certainly the more important of the two that we'll be talking about. Ionization energy is just exactly how it sounds. It's the energy that it takes to create an ion, and specifically to create a positively charged ion. So basically, it's the amount of energy required to form a positive ion. So it's how much energy it takes to remove an electron from the ground state of an atom. So we've got ionization. So we've got a regular old atom. So let's say here's our nucleus, and here we've got some electrons out here. It's how much energy it would take to take one of these electrons and remove it from an atom. Okay, and that's just referred to as ionization energy. When we talk about the first ionization energy, sometimes written as I1, it's the energy that would be needed to remove the first electron. If we talked about the second ionization energy, it'd be the energy to remove the second electron. Third ionization energy, removing the third electron, and so forth. Now, how would you write that? And this actually did appear on the exam a while ago. There was a question relating to, I think it was sodium or something like that, or I don't know what element it was. But the question was, it takes 1,681 kilojoules per mole of energy to remove an electron from a sodium atom. Write the equation that shows the ionization of sodium. And this is what you had to write. You had to write sodium becoming a sodium ion plus an electron, removing that electron. Okay, obviously removing the second electron is you would be starting with a sodium ion, and then you'd be removing another electron. So now it would become Na2+. The bigger the number, so the bigger the amount. So let's say it's 1,681 kilojoules as opposed to 2,542. The bigger the number, obviously the more difficult or the more energy it takes to remove an electron from the atom. And then certainly the more electrons you remove, the more difficult it becomes to remove the next one. Once you take this electron away, remember sodium's still got 11 protons. So whether you remove one electron or two electrons or whatever, it's still got 11 protons. So every time you take an electron away, it becomes more, the ionization energy increases more and more. Okay, and this is actually the question. It was write the equation for the ionization of atomic chlorine that requires 1,251 kilojoules per mole. Okay, and so that would be, now it's not molecular chlorine, it's atomic chlorine. Atomic chlorine means an atom of chlorine. So you're going to have Cl becoming Cl plus 1 electron. And then you could put the enthalpy change equals negative 1,002. But they did not expect you to do that. They really just wanted to see that right there. Okay, so here is a table that kind of shows you this trend in ionization energies. Notice that sodium has one valence electron, and so you can remove one electron without seeing a big jump. Once you remove that second electron from sodium, you see a big jump in ionization energy. What that jump tells you is that sodium's only got one valence electron. Notice magnesium. Magnesium, again, same thing. 700 kilojoules, 1,400 kilojoules, 7,000 kilojoules. These two are valence electrons. So magnesium, again, here's the nucleus. It's got the 1s2, 2s2, 2p6, 4, 5, 6, and then 3s2. So you can remove this one, not too difficult because it's a valence electron. You can remove this one, again, not too difficult because it's a valence electron. But once you get rid of these two, once you hit the third ionization energy of magnesium, you're trying to take away the third electron. Now you're getting to the core electrons. The valence ones are gone. So the shield, all of that shielding that was taking place is now gone, and these electrons are a lot closer to the nucleus. So once you reach a core electron, and these are all once you reach the core electrons, you can see there's a huge jump. Look on sulfur, you go from 8,500 to 27,000. So you can remove valence electrons without too much energy, but once you jump to those inner electrons, those core electrons, is when you see that big jump. Okay, now this also helps us. The reason that these numbers are so important is because it helps us understand the idea that only the outermost electrons, or those valence electrons, are involved in the sharing and transfer of electrons when a chemical reaction occurs. It just takes too much energy to remove these other electrons that it's not thermodynamically very feasible for that to occur. Those inner electrons are too tightly bound to the nucleus to be involved in chemical reactions. Now, how might you see this on the exam? Old questions that I've seen is they might have, 5 different elements, and they'll say, here's the ionization energy for one of these 5 elements. And it'll have, maybe this, it'll say ionization 1 is this, ionization 2 is this, 3, 4, and 5 is this. And then they'll say identify the element. And what you have to do is you have to look for the big jump in the ionization energy data. Here we see the big jump from 4,000 to 16,000. And so what you would have to do is you'd have to go, okay, this element has 1, 2, 3, 4 valence electrons, and this is a core electron. So only one of the 5 choices they'll give you will have those 4 elements there. Okay, so here we can see kind of a graph of this, that as you go across the periodic table, you can see that it's going up. As you go down the periodic table, we can see it's going down. And we'll talk about why that is here in just a second. But that's just a graph of different ionization energies. Okay, so as you go, it looks like we're missing a slide here. But basically it's telling you that as you go from left to right, basically it's telling you that as you go from left to right on the periodic table, the ionization energy increases. And I'm not sure how we missed that. But as you go from left to right, the ionization energy increases. This is due to the fact that as you move from left to right, the number of protons increases. However, all the atoms are still shielded by the same number of core electrons. That sounds just like atomic radius. It sounds just like effective nuclear charge. If you explain this in terms of effective nuclear charge, it works just fine. As you go from left to right, the ionization energy increases. So as you go from sodium to magnesium and then all the way over to chlorine, the ionization energy goes up because you're increasing the number of protons, which means the electrons are more attracted to the nucleus. Okay, the more the electrons are attracted to the nucleus, the more energy it takes to remove them. So the nuclear charge increases, or you could say the effective nuclear charge increases. The number of core electrons remain the same. Therefore, the valence electrons feel a greater attraction to the nucleus, which makes it more difficult or requires more energy to remove those electrons. Okay, an easy way to look at that is compare the number of shielding electrons and protons, or the effective nuclear charge, in sodium and chlorine. Sodium has 11 protons, chlorine has 17 protons. They both have 10 core electrons. Okay, overall effective nuclear charge +1, overall effective nuclear charge +7. Okay, big difference. These electrons in chlorine are more attracted to the nucleus. The more they're attracted to the nucleus, the more energy it's going to take to pull them away. Imagine that with magnets. If one magnet is more attracted to something than another magnet, it's going to take you more energy to pull that magnet away than the other one. Okay, so here was something from an old exam. Oops. It says, as shown in the table below, the first ionization energies of silicon, phosphorus, and chlorine show a trend. From silicon, it's 786. Phosphorus, it goes up to 1012. And then from phosphorus to chlorine, it goes to 1251. If you notice, if you look at the periodic table with these 3 elements, you can see that they skipped one. They go silicon to phosphorus, and then they skip sulfur, and they go right to chlorine. And the reason that they do that, if we come back to that graph that we saw, right here, we can see that, for example, here's sodium, magnesium is right here, aluminum is now down a little bit. Notice that as you go from the 3s, so these 2 right here, the 3s to the 3p, it drops a little bit. Okay, that's because we're increasing the energy. We're going to a higher orbital from 3s to 3p. And then notice here, this right here would be aluminum, this is silicon, and then this is phosphorus right here. If that's phosphorus right there, with phosphorus you have a half-filled subshell. You've got, if you look at the orbital diagram for phosphorus, phosphorus is that 3p, and it has a half filled. That is stable. Okay, once you add that next electron right here, that decreases the stability, so you see a little bit of a drop right there, and it happens here. It happens in most cases. It happens right there as well. You can see that that's very common for it to occur, because again, you've got that half-filled subshell. That is a very stable configuration. Then when you add this next one, you're making it back to being unstable, a little bit less stable. So you see that little drop in ionization energy. Okay, so they want you to basically explain it says explain the reasons for the trend in first ionization energies. So you could say, again, silicon to chlorine, you're going from left to right across the periodic table. Again, notice this. Oh, they don't say it, but a lot of times below this they'll say, note, explanations based on position of the periodic table are awarded no points. Okay, so they say 1 point is earned for explaining that greater ionization is due to increased nuclear charge. So all they really wanted you to say is that chlorine has more protons. They would give you credit for that, it says. However, probably a better way to explain it would be something to the effect of, yes, chlorine does have more protons. I would certainly also want to mention something about the electrons, that the core electrons do remain the same. So they say because the valence electrons in all three elements are shielded by the same number of inner core electrons, so again, that's important. The nuclear charge increases going from silicon to phosphorus to chlorine. The valence electrons feel an increasing attraction to the nucleus. The valence electrons having a greater attraction to the nucleus will be more difficult to remove, so chlorine has a higher ionization energy. Okay, certainly, again, this is the perfect answer. You would certainly not include that much information if you simply just said that chlorine has the most protons. However, they all have the same number of core electrons. Don't say total electrons, because they don't have the same number of total electrons. They have the same number of core electrons. More protons means more attraction to the nucleus, which will make it more difficult to remove an electron from. Okay, as we can see from on that previous graph as well, that as we go down the group on the periodic table, the ionization energy decreases. So as you go from sodium to potassium to rubidium, as you go down, the ionization energy also goes down, which means it's easier to remove an electron. As you go down, the principal quantum number increases. Again, important to mention that, which places the electrons farther away from the nucleus. We talked about that with size of atoms, that as you go down, the size gets bigger. The farther electrons are away from the nucleus, the weaker the attraction, which results in a lower ionization energy. That seems to make pretty good sense. Okay, so here was a question from a while ago. The first ionization energy of potassium is less than that of sodium. So you look at the periodic table, you see that potassium is lower than sodium, and you would want to say, first of all, referring to the size. So you would want to say something about the principal quantum number. That both sodium and potassium have an S1 valence shell electron configuration, but the potassium atom has a higher, and that N is the principal. I'm not sure why they put it that way. But you would want to say that potassium has a higher principal quantum number, therefore it's a bigger atom. So that gives you that point right there. And then you would have to talk about, well, why just because it's bigger does that affect it? Because the higher the principal quantum number, the farther the electrons are from the nucleus than sodium. The greater distance, just think about planets, think about Pluto. The greater the distance, the greater the less the attraction. My pen's not working. So the greater the distance, the greater the weaker the attraction. So because its valence electron is less attracted to the nucleus, then certainly it's going to have a lower ionization energy. So here's just a graph of that. You can see, again, notice here's lithium, here's beryllium, that as you go across, it goes up. Notice again, there's that little drop as you go from 2s to 2p. I doubt they would ask you something on the exam about that. Boron, carbon, nitrogen going up. Again, a little drop as you, again, with nitrogen, you've got that 2p orbital halfway filled. With oxygen, you're messing up that half-filled subshell. And then again, as you go oxygen, fluorine, neon, it continues to go up. And then as you go down, you can see there is that drop, increase in the principal quantum number, more electrons to attract. And then this part, not too big of a deal. The last part is certainly much more important, but you should certainly be aware of what this refers to. Electron affinity is when atoms gain electrons to form anions. So it's the energy change associated with an electron being added to a gaseous atom. So if we were so how would you write that equation? It'd basically be the opposite of the other one. The other one was going from chlorine to Cl plus an electron. Here, because you're gaining an electron, you would write it as a reactant to make Cl minus as your product. The noble gases, do they want to gain an electron? No, they do not. So typically they have a very positive electron affinity. The alkaline earth metals, they have a completely filled 2s subshell, also typically have a positive electron affinity, because every time you add an electron to it, see, they're positive, because if you add an electron to it, you're adding, like if you add an electron to beryllium, you're adding it, instead of having 2s, you're now up to 2p. You're adding it to a higher energy. Argon, same thing. You add one to argon, and it's going up here into the 4s. So here you're at 3p filled. You add another electron. Typically, though, you can add an electron without too much difficulty. Obviously, the halogens are very negative. They release a lot of energy. Remember, the negative is like exothermic. It's releasing energy. When it releases energy, obviously it's getting hotter, we could say. But it's a very negative value because it wants to have more of that. It really wants that electron to become like a noble gas. Okay, these ones can actually take an electron as well because they all have that S1 configuration. They can take another electron without too much energy. It's just these guys going up to here, and then the noble gases going up to the new s orbitals. Okay, so not too much here. There is certainly more in the packet, and I think pretty much all of these questions deal with ionization energy. Very little about electron affinity. So just a few from the book. Make sure on 41B and E that you do explain your answer, because that's what they're going to have you do on the exam.